Okay, on with the talk. So I want to concentrate on this topic that kind of obsessed me for the last few years now of can we identify potential tipping points of climate change? In fact, what I call the tipping elements in the climate system. Are there large parts of the planet that as we warm the world up and transform the climate system, they may pass a threshold at which they're committed to change into another state? And these changes may well be dangerous for us and for other living things that we share the planet with. So I think we're all quite familiar with the notion that the world is steadily warming, and I was in a way motivated to try and address what I saw as something of a gap in our analysis of the Intergovernmental Panel on Climate Change and their very authoritative reports, that there is very little emphasis on these possible threshold changes that we're learning more and more about. And I want to look particularly about whether there are early warning signals for abrupt changes. Actually, on my map is something that already happened. It isn't strictly about the climate, although it's connected to the climate system, and that's the Antarctic ozone hole caused by emissions of chlorofluorocarbons. And it's actually one of many examples that is summarized in a nice report by the European Environment Agency of past cases where usually some scientist somewhere gives an early warning that some new chemical or pollutant may be dangerous. But very rarely do we as a society or societies heed these warnings. In the case of the ozone hole, it was recognized that chlorine and fluorine containing gases would destroy ozone and were potentially dangerous, and papers were published on this even as far back as the late 1920s. And ironically, in that case, the satellites were actually observing the ozone hole, and the data was being thrown away at the time because it was regarded to be unreasonable. And it wasn't until a group of British scientists actually on the ground at the British Antarctic Survey Station detected the ozone hole from below and published a paper on that it was realized that the satellites had been seeing it all along and we had a major problem on our hands. So let's hope we don't do quite as badly with climate change, because the stakes are even higher. So I want to talk about what are the possible tipping points of climate change, or tipping elements in the climate system. I want to talk about what would be some quite general methods of early warning of a system approaching an abrupt change, and can we get them to work on the climate system. I'll show that you can test these methods on past abrupt climate changes and in models, and they work quite well. And then I will try to apply the methods to the region where I see the most abrupt changes unfolding in the climate, and that's in the Arctic, and particularly with the retreat of the sea ice, for which we also have a fantastic satellite record, at least from about 1979, so when I was 6 years old onwards, a daily record of the Arctic sea ice cover. So first of all, let me introduce how we conceptualize the idea of a tipping point in the climate, because this is a very fashionable bit of language, at least in English. You hear politicians talking about tipping points all the time, and a guy called Malcolm Gladwell, a staff writer at The New Yorker, wrote an excellent book on the tipping point in 2000, became an international bestseller. In fact, the subtitle of the book is the idea that little things can sometimes make a big difference to the state or the fate of some system. Gladwell's very interested in human affairs and past abrupt changes in human societies. I'm interested in the climate system, and so we tried, a group of us, to pin down a firmer definition, if you like, of what might constitute a tipping point in the climate. And we decided we should try to identify what I call the tipping elements in the climate system, the bits of the planet that are at least subcontinental in scale, so like at least 1,000 kilometers by 1,000 kilometers kind of scale, that could be switched under particular circumstances into a qualitatively different state by a relatively small perturbation, like a little bit of extra warming could make the difference for whether the Greenland ice sheet stays with us, or a little bit of extra warming might make it melt away in the long term. And then the tipping point is what we'd call in physics the critical point in forcing and in some feature of the system, so in, say, temperature or in ice volume on Greenland, at which the future state of that system is altered. It's qualitatively altered, whether you go past that point or not. So that sounds very formal, and this is in a sense I put this slide in to talk about the range of future global warming, which I would call like the accessible neighborhood of temperatures or climates that we're going to reach this century. But it's also a reminder, because this is the IPCC's own favorite figure of past warming up to the present, which is now just about 0.8 to 1 degree, and then future trajectories, which, as you can see, we can ignore this one. This is the warming commitment if you could magically freeze the concentration of greenhouse gases in the atmosphere at the year 2000, which undoubtedly you can't, and we didn't. But even if you did, you'd still get some more warming, another 0.6 of a degree or so. Of course, we've continued to increase the loading of this blanket of heat-trapping gases in the atmosphere, and these different color bars are just different amounts of future fossil fuel burning, essentially. And then there are some better estimates of the error ranges over here, which tell you that we could be, relative to the year 2000, we could be between about 1.5 and about 6 degrees warmer by the end of the century. And that is well, at the upper end, that is a shocking change. That's more, 6 degrees of warming is a bigger temperature difference than the difference between now and the depths of the last ice age, when the sea levels are 150 meters lower and there are massive ice sheets on the northern hemisphere, etc. So we can perhaps anticipate that if we go into this region, there are going to be some very, very, very significant changes in the planetary machinery, and that's what the talk is about, really. What might they be? And to narrow it down a bit, well, we have the idea that in Earth history there have been many abrupt changes in the system, but if we want to talk to policymakers and focus their attention, or talk about this cogently as scientists, we want to think about what are the most policy relevant potential tipping elements or tipping points. So they should be the things where we're going to tip them potentially this century, is what I said, within what I rather ambitiously called a political time horizon of 100 years. Of course, most politicians only think about 5 years ahead until the next election, but the IPCC, as you'll see, and others in this game, we often think on the century timescale. So I want to think about systems we might tip this century, and ones that it could take longer for them to actually undergo a change. If they're a big ice sheet, like the ice sheet on Greenland, it may take several centuries to melt that. And so I want to include the systems where the qualitative change in the system plays out within what I'll call an ethical time horizon of order 1,000 years. And I picked that sort of out of the air because I come from a city, Exeter, that was there 1,000 years ago. It was a Roman, it had been a Roman settlement, in fact, and it was still thriving 1,000 years ago. I'm very used to my home capital of London, which was also a thriving place 1,000 years ago. So we should be able to conceive of the world in some sense 1,000 years hence. We have no idea what it will look like, but we may have some ethical kind of relationship even that far ahead. And finally, a lot of people need to care about these systems for them to make it onto my map, which looks like this. And so this is what we identified as a sort of short list of potential tipping elements in the climate system that could be passed. Well, that was the one that's already passed. The other ones are things that could be passed this century and would undergo a qualitative change within 1,000 years, and some of them an awful lot quicker. So if we disrupt monsoons in India or West Africa, that could play out from 1 year to the next. So the time scale of these response to these systems differs radically. In the case of if we trigger a dieback of the Amazon rainforest, that would unfold over decades, I would say. Other changes, as I mentioned in the ice sheets, are the slowest ones. And it's Greenland and West Antarctica that pose the biggest risks. So the point I guess I take from this map is there's quite a few potential tipping elements and tipping points in the climate system. It's not just like one thing. In the literature, there's an awful lot of discussion about the potential for collapse of the Atlantic overturning circulation, but there's of the order of 10 different tipping points out there potentially this century. And we should have, of course, the natural thing to do is to ask first, which ones are closest? And as usual, we are uncertain about that. And frankly, there's always some uncertainty in this area of science for reasons I can elaborate on in the discussion session. But even back in 5 years ago, we could have a go at ranking roughly where the thresholds lie for different tipping elements in terms of global warming above the 2000 level. And the grey in the background is the expected range in the year 2100, the end of the century. And I use some sort of burning embers, some sort of colour scale here. Going from white to yellow is going from no probability to some probability of tipping a system, and going into the darker red means more likely than not that you've tipped it. In this case, loss of the Arctic summer sea ice cover. Here it would be committing the Greenland ice sheet to an irreversible meltdown, which eventually gives us 6 or 7 meters of sea level rise, which is a serious issue. This, by the way, a collapse of what's sometimes called the thermohaline circulation of the ocean, is like the poster child of abrupt climate change. And that's happened in the past. It's been linked to past abrupt climate changes I'll talk about in a minute. But in terms of the future, our best understanding as of a few years ago was that actually might be the most distant of these thresholds, interestingly. So not all of these will turn out to be tipping points, but I suspect some will. And some may be closer than mapped here. And I'll come back later in the talk to looking at what's happening to the Arctic sea ice, which is perhaps the nearest threshold. The only other thing I want to say about what we know about where these thresholds are is that there was a quite detailed so-called expert elicitation exercise conducted that started at a workshop we organized back in 2006. And this looks very complicated, but what you have is a number of experts, about 50 scientists around the world, were offered 3 different future temperature ranges. This is less than 2 degrees global warming, 2 to 4 degrees of global warming, above 4 degrees. And for 5 different tipping elements, as I call them, the Atlantic overturning circulation, the Greenland ice sheet, West Antarctic ice sheet, Amazon rainforest, El Nino phenomenon, they were asked to give their assessment of the probability of passing a tipping point under each of these 3 warming corridors. So not everybody answered for every system, but you have these funny black bars. These are imprecise probability ranges between 0 always and 1 at the top on the y-axis of the likelihood of tipping these different systems. Maybe I'll concentrate on Greenland because it's the most shocking one. Even in a less than 2 degrees of warming world, there are experts saying that it's as likely as not, or perhaps more likely than not, that we commit the Greenland ice sheet to a long-term meltdown and get those 6 or 7 meters of sea level rise. If you go, and these color bars, by the way, are aggregating the different expert responses. So if we go to a 2 to 4 degrees warming world, which is as a minimum where we're heading, then it's looking as likely as not, if not more likely than not, that we lose Greenland. And in a high warming world, which is kind of business as usual, then more likely than not. So you can do some fancy maths and combine all of these imprecise probability statements. What you come out with is in medium warming, there's an absolute minimum, under the most conservative assumptions, at minimum 16% probability of tipping one of these systems. And in high warming world, which I would say is the trajectory we're on, at the moment, it's minimum 56% probability. In other words, it's more likely than not that we pass a large-scale tipping point in the climate system. So that is important because all our economic models of climate change at the moment assume that these events are high impact but low probability. And what these experts are saying very clearly is they are both, if we carry on these trajectories, these kind of events will be high impact, high probability. And that should profoundly change our economic analysis and our personal analysis of the risks posed by climate change. So that might have been a little bit long. That was the warm-up to tell you about the field. And now I want to talk about, okay, can we get any, if we think that these high-impact changes lurk ahead, can we get any early warning signals before we reach them? And I want to talk about a couple of methods we've been developing to both detect and hope, and in principle, provide early warning for an approaching tipping point. So to do this, I'm first going to talk about 2 cartoon types of tipping point. This is the kind of way that many scientists would draw a tipping point for a system where there's one stable state up here as a function of some control or some forcing. You could think of this as, say, global temperature change. And there's another stable state for this system down here, and there's an unstable branch here. This might be with a Greenland ice sheet, without a Greenland ice sheet. It could be with Arctic summer sea ice cover or without. It could be a strong Atlantic overturning circulation or a collapsed circulation. But these kind of systems have what we call fold bifurcation points, tipping points where if we get to somewhere over here and we nudge a little bit further to the right, perhaps with global warming, the system could undergo abrupt transition into its other stable state, and you'd have to work very hard to recover the original state. You have to turn the forcing down a lot more to get back to where you started, and then we talk about that as a hysteresis loop in the system. These kind of tipping points probably are out there. They're the kind of the worst sort because they have carry this element of irreversibility, but also on the good side, if they exist, they should carry early warning signals as we go to the right along this branch, and I'll come back to that in a minute. But out there in the climate system, there's also a lot of internal variability, and it can be the case, and it appears to have been the case in the past, that sometimes without moving on this x-axis, which you might think of in cartoon terms as global temperature, you can occasionally get knocked out of one state and end up rolling, if you like, into another stable state, just thanks to purely internal variability in the climate system. And that's what we call a noise-induced tipping or change in the language. And I'm afraid if there's really no movement on the x-axis, there's no early warning for these kind of events. And I introduce them because they turn out to be quite a good way of characterizing past abrupt climate changes on the planet as these noise-induced tips. And what we're talking about in cartoon terms is if we're in a system with, say, two states available, we can only ever be in one of them, but occasionally if we imagine it ourselves as a ball rolling around in this energy landscape, occasionally you could get tipped over this hill here and roll off into the other state. Now, if we have a climate system like that, and we have lots of variability in it, the idea of our first method is that we can actually diagnose how many valleys or how many states there are in the system. And this is like a cartoon test of our method, which I don't have time to explain to you fully, but it's actually quite simple. And here's a cartoon system where we changed it from one state to two stable states to 3 to 4, and we generated some time series of realization of what the ball is doing rolling around in this changing landscape. And that's what you get as a time series where this axis becomes this one. And it's maybe not so obvious when you get over here that there are 4 states lurking in this system. It looks more like 1, 2 maybe. But down here at the bottom in the colors is what our method detects for the number of states. When it's presented with just this time series, it can back out a good estimate of that the system has 1 state initially, and at around this point here, it switches to having 2 states, 3 states, 4 states. The y-axis, this is time. The y-axis here is just the size of the window or sliding window you put on this time series. So how big a window do you slide along the time series to try and back out how many states? And really all I want you to do is remember the colors, particularly that red means 1 state and green means 2 states. Because when we go to the past climate record, here we have, let's start up at the top. Here we have 2 different ice core records from Greenland, from 60,000 years ago right up to the present. You can see they're quite similar. One is from the summit of Greenland, the Grip ice core. One is 325 kilometers away to the north, but still on the summit ridge of Greenland. So this is from the last ice age, or the middle of it over here, through to the current warm interglacial, the nice stable climate all our civilizations, agriculture, etc. has been developing in, the Holocene as we call it. You can see in the last ice age, first of all, that there are lots of abrupt changes. And the y-axis here is what we can think of as a proxy for temperature, in simple terms. So there are repeatedly abrupt warming events followed by a slower cooling and then another abrupt warming and so on. And there are over 20 of these events in the ice core record in Greenland. As we come out of the last ice age, there's a very abrupt warming here. It's known as the Bolling warming into the Bolling Alerod. Then it falls colder again into what's known as the Younger Dryas, and then it abruptly warms into this stable Holocene that we've been enjoying for 10,000 years. Now, my method I was telling you about actually does a reasonable job of backing out how many states are there in the system as we run through time here. And remember, the colors say that, okay, most of the time down here in the Ice Age, there are 2 states to the climate system. Interestingly, at what's called the last glacial maximum, the coldest interval, it looks like there's only 1 state in the climate. Then as we come out of the Ice Age, there are at least 2 states again, warm and cold, if you like. And the current interglacial is characterized as just 1 stable state. You can then reconstruct these kind of energy landscapes, valleys and hills, to describe the climate. And in short, what it shows is that over time, you have a system where initially the warmer climate stage is the more stable one, and the colder one is less stable. Then as we go deeper into the Ice Age, the cold state gets more stable, the warm state less stable. Eventually, the warm state disappears temporarily in the depths of the last Ice Age, 20-odd thousand years ago, and then it reappears as we come out of the Ice Age, and then the cold state disappears, or it certainly isn't sampled in the last 10,000 years. All sounds very complicated, but the take-home message is, in the past, the climate has changed abruptly, and we're talking about 8 degrees of warming within a decade in Greenland, and potentially across large parts of the Northern Hemisphere. So that is really striking climate changes. These past abrupt events can be, in some sense, characterized as like a ball being knocked between the 2 valleys. But as we look over time, as in this case the Earth's orbit around the Sun is changing, then the number of states in the climate system and their relative stability or instability actually changes over time. And occasionally we have what I described as a bifurcation point, which is like a state here, the warm one, losing its stability and disappearing, or a new state appearing, or that's the warm state reappearing. So we have in the past both these noise-induced tipping and these bifurcation tipping points. And we should probably therefore expect these kind of changes as we go into the future, probably a bit of both. The ones I'm really interested in are where we have what I've called, or in the mathematical language, is called a bifurcation point. So here's a case, a cartoon, where a system starts, this could be Arctic sea ice cover, which we'll come to in a minute. There could be more, a state with more summer Arctic sea ice cover here and less over here. And as the system is forced, it may be that the state with more ice cover loses its stability at this point. And although that was the state we were in with a sort of solid red ball, when you get to this point, the ball has to roll off to the left and go into the other state in an irreversible tipping point. And the interesting idea here is that there are some very general features of how a system should behave if it's undergoing this kind of approaching this kind of tipping point. I've sketched on here a kind of dotted line showing you how curved is the valley at its bottom there. And that's the thing, in a sense, we want to monitor. You could imagine the climate here as being really the long-term average behavior of what you think of as the weather day to day. And the weather in the climate and in this paradigm we treat as a short timescale, fast, essentially random process. But you can think of it as nudging the climate ball around all the time. And we can watch the ball try to roll back to its lowest energy state, which is what it wants to do. And we can watch that in the form of a time series of climate data. And the simple idea you should be able to see from the cartoon is that as you approach the tipping point, the state you're in, it gets shallower and the ball is going to roll back slower from any given nudge. And that behavior is called slowing down or critical slowing down. It's actually seen arguably it's seen in humans as we're approaching certain critical transitions. People have looked at heart attacks and epileptic seizures, but I'm interested in the climate system. So what we should look for is slowing down in response to natural fluctuations as a warning that we're approaching a bifurcation tipping point. And we might also expect that the ball is going to move further for a given nudge as the well here, the valley, gets shallower. And that should be seen as more variability in the system, right? You should see greater variability in your climate index as an early warning signal. So those are the basic ideas. We look for slowing down, and we maybe also look for that accompanied by increasing variability as an early warning. And now I return to my example of the Ice Age. Here I'm looking at a subset of what we had before, from 22,000 years ago to the end of the Younger Dryas, just before there's an abrupt warming into the 10,000-year stable interglacial we're living in now. I've cut out the final abrupt transition because if I include that, it's going to influence the indicators I'm looking at. And what I want to look for is if I just take out the red line here, which is a sort of underlying trend in the data, and I look at the anomalies around it, I'm looking for, is the system slowing down as an early warning that the end of the Ice Age is coming. And in simple terms, if you just look at this by eye, you can see that the fluctuations over here are much more persistent, and the system is a lot more sluggish over here than it was back there in the depths of the last Ice Age. So in very simple terms, it's obvious that the climate system was slowing down before the end of the last Ice Age, and that was the expected early warning signal. And if the people alive at the time had a more advanced science and these methods, in a sense, they should have been able to see what was coming. How do we actually measure the slowing down? That's a technical matter, but the simplest way to do it is you're looking for correlations, in this case in a time series of data. So and the simplest way of doing that is you look at what's called lag 1 autocorrelation. So you ask yourself how much like yesterday is today, and how much like today is tomorrow, if you like. And as the system slows down, today should become more like yesterday, and tomorrow will be more like today. So you'll see this quantity, the lag 1 autocorrelation, rising, and that's what this is down here. This is a rising autocorrelation in the data, showing the slowing down. So all of that was to say that we can test these methods that should work in a general sense on past abrupt climate changes, and we find them working there reasonably well. So these general early warning signals do show up before past abrupt climate changes. We've shown that they work in various model experiments as well. I can force my climate model towards a collapse of the Atlantic overturning circulation, and I get a very good early warning signal before that. Then now the question is, can we apply these methods in any useful way to real climate data up to the present and see if there are any early warning signals that abrupt changes lie ahead? And for that, I want to finish by looking at what's happening in the Arctic, because the Arctic is, if you like, the what's called the canary in the coal mine, or the bellwether, or the place that's showing the first signs of abrupt and potentially dangerous climate change, and should warn the rest of the world about what's coming, in a sense. And in the Arctic, we see warming that's around 3 times the global average, and we see iconic things going on, like in particular the Arctic sea ice retreating very rapidly, especially in its aerial coverage in summer, but also in its thickness and volume. And it's the Arctic sea ice I'm going to concentrate on, although there are lots of coupled systems in this region, many of which are thought to exhibit threshold behavior. So first of all, we can take the long view, because a group has just published an attempt to back out the interannual variability in the summer minimum Arctic sea ice cover for over a century. And we see overall it's declining. We knew that already from our short satellite record over here. But actually, if you look, it's pretty obvious by eye, but if you take out the trend and look at the data, the variability is going up. The variance in this time series is going up. This complicated thing over here is just showing that that's a very robust trend here, regardless of the size of the sliding window I use on the data or the filtering I use to get rid of the trend. So it's just to convince myself that this is a robust upward trend. And that is one of the things we're expecting for a system approaching a threshold. It becomes more variable. So we can give that a tick for the Arctic sea ice. Now let's turn to the really attractive data set in a way, the very amazing data set that's existed almost as long as I have, and that's this satellite-derived Arctic sea ice area cover. So that's now over 30 years of data, and it's pretty much daily resolution throughout, with a few gaps early on which you can fill, as it were, to get a complete even time series. And you see that the sea ice has a huge seasonal cycle between its winter maxima and its summer minima. And ultimately, we're going to want to remove that cycle and look at the residuals. But even if I just look at that by eye, something happens in 2007. The summer minimum drops down and it sort of stays down, whereas the winter maximum doesn't show the same abrupt shift. And if I just plot in red the winter maximum on the left-hand scale up here, and in blue the summer minimum on the right-hand scale, and I've shifted the scales so I can overlay them, you see 2007, abrupt jump in the amplitude of the seasonal cycle of the sea ice of the order of 1 million or 2 million kilometers squared, so a big area, and that has persisted ever since. So in a nutshell, that's what I think we've already detected as a potential tipping point in the sea ice. It's not the complete loss of the summer sea ice, but it's a large region, a large chunk that's kind of gone and added to the annual variability. Now what we've done here is what you'll find if you go on the web and you look at a website like the Cryosphere Today, you'll see a record of the sea ice as an anomaly relative to the mean seasonal cycle. So you take out all that sinusoidal seasonal variability and you look at what we'd call the residuals, and there's an overall downward trend that we know about, and there's the record minimum in 2007, and in fact all the last 5 years have seen the 5 lowest minima in the sea ice record, 2007, 8, 9, 10 and 11. And now we run the methods I tried to explain or introduce briefly. First of all, we can run our method that tries to say how many states do we characterize this system as. And this one says most of the time, it's a bit messy, but most of the time that's a system with one state. But when we get past 2007, green becomes a more dominant feature. This is saying that this is best characterized as a system with 2 states. In other words, a new ice cover state has appeared in the sea ice in the last 5 years and has persisted, and it's a lower ice cover state, basically. To look at that in more detail, you can take these white dot points, that is, take 4-year chunks of this time series, divide it up into 4-year chunks, and try and reconstruct the energy landscape as I talk about it for the sea ice. And you have a system with one state, one state, one state, one state, one state, maybe hints of a higher ice cover state there, one state, hints of a lower ice cover state here, and then a system in the last 4 years characterized as having a couple of states. So these plots down here, these are just the data, histogram of the data for this interval, then this interval, and finally that interval, the last 4 years. This chunk here includes the record minimum in 2007. So that shows the hints of another mode in the data, another mode in the histogram, another state of the sea ice appearing. Here, well, you might argue there are 3 states, but there's certainly not a system with one stable state. So we're saying that the Arctic sea ice has passed the tipping point. It did so in 2007, and now it's better characterized as a system that's switching under internal variability between 2 different states as it goes through the seasonal cycle. You should ask then, okay, are there any early warning signals before this happened? And the bad news is they don't seem to work particularly well. So the attempts to look at slowing down in this time series, we don't really see it if we look at the lag 1 correlations. That was literally from day to day in this time series. So today does not get more like yesterday in the sea ice as you approach 2007. In fact, it gets less like yesterday. This indicator goes down. That probably isn't, you shouldn't take that to heart too much, because what we really want to find here is how is the slowest time scale of this system, the sea ice, behaving? So we should be looking at longer timescales in a day, because the sea ice has what I'd call memory, and you want to look more on a seasonal timescale, like 100 out to 100 days. And that's what we do with this other indicator down here. We look at how correlations are behaving on 10 to 100 day timescales, and that sort of has a bit of upward trend in here, but still it's not hugely convincing. Overall, if we include what's happened recently, it has an upward trend, but the early warning isn't working brilliantly for this system. So, and we shouldn't expect it to work perfectly in every case, but still the detection is there that we think something abrupt changed in 2007. So I just want to finish by giving a little cartoon of what I think is going on for this system, where I'm going to use my earlier kind of bifurcation cartoon, but now it's a much smaller fold in the States. And before 2007, early on in the record, imagine the sea ice has a maximum cover up here. Let's say it undergoes a lot of seasonal forcing, so the lights come on in the summer, they go off in the winter, you have darkness 24 hours for a long period of the year. And that causes, so we have darkness in the winter, we have full daylight in the summer, we have a maximum and a minimum seasonal cycle of sea ice cover. It fluctuates like this. But with global climate change, the idea is we're moving to the right on the forcing axis. And initially, that doesn't do a great deal. We move the maximum down, we move the minimum down by a similar amount. We have the same amplitude of seasonal fluctuation. But the cartoon version of what happened in 2007 and since is that we passed a point where the summer minimum cover dropped down abruptly, and there was an extra 1 million or 2 million kilometers squared of sea ice loss in the peak summer solar heating, if you like. But of course, as you went back, as the lights went out, you went back through the autumn into the winter, the system recovered back onto its original branch every autumn or winter. But the amplitude of the seasonal cycle jumped up, which is exactly what we saw in the data. So that's the cartoon of what I think a tipping point that might already have been passed in the Arctic. And finally, okay, I've spent the whole lecture talking about can we get better information on the likelihood of these different climate tipping points. That's kind of a natural thing to do as a scientist. But we should also be asking ourselves, what are the impacts if we do pass them? Because if you're a policymaker, certainly in the UK, the British government spend a lot of time sat down trying to draw out risks, future risks, on axes of likelihood and impact, where the biggest risks are formally risk is the multiplication of likelihood and impact. So the biggest risks are up here in the right, and the smallest risks are down here. And policymakers really want to know what's lurking up here. At the moment, I've drawn my loss of sea ice very likely. I think it might, in some ways, it's already happening, but its relative impact is perhaps the lowest. That's not to say that it doesn't have really important impacts. In fact, the loss of the summer Arctic sea ice has been linked to recent cold winter extremes where I come from in Europe and other parts of northern and central Europe. But what I would say is that if anyone wants a research agenda, we should be going to work trying to quantify what will be the impacts if we do pass some of these tipping points, because there's virtually no work on that in the literature, except for the Atlantic overturning circulation and a tiny bit of work on the loss of big ice sheets. So I may have gone on too long, but I tried to convince you that there are several tipping elements in the climate system that could be triggered this century by our activities, anthropogenic forcing as we call it. Some of these could become high impact, high probability events, but we need improved information on their likelihood. But this bit is key, because if that's true, we have to fundamentally revise our approach to the climate problem as a risk management problem. Early warning methods exist for at least some types of tipping points, those ones that we can think of mathematically as like bifurcations, and they've been successfully tested, or at least I think we've successfully tested them. They're the same methods as sort of detecting a recent tipping point in the Arctic sea ice cover with the appearance of a new lower ice cover state. At the moment, I can't put my hand on my heart and say we got a robust early warning of that, but we'll keep working on it. Thank you very much.